In this example, we will look at modeling with first-order differential equations. I had mentioned in our last video that there are many first-order differential equations that can't really be solved. And what we do have, though, is a number that can be solved. So we'll be looking at those examples. We'll look at the mathematical modeling, which is a physical situation is translated into mathematical terms. And if the mathematical statement involves a rate of change, a differential equation might become the mathematical model of the process. Mathematical models are evaluated by comparing their predictions with the experimental results. The four different models we will look at, one is mixing. So there's a solution in a tank, and then we're introducing a new concentration of a solution in that tank while the tank is simultaneously being drained. We also have compound interest, which is extremely applicable to you who will be earning an income. We have chemicals in a pond, very similar to mixing. And then finally, we have an escape velocity for anyone who wants to be working at NASA. I'm going to mention that setting up these first three equations should not be that difficult. And if you've had some physics, the fourth one isn't that difficult either. So I would suggest you give it a try. You know, if you need some help, then don't feel bad about looking at it. Of course, you shouldn't feel bad about that, looking at how it's set up. But once we get to the differential equation, you really should have enough knowledge from the previous videos to just work it out and solve it. So give that a try. Of course, I won't judge if you look at how I did it because one, well, that's the whole point of me making a video, is in case you get stuck, you have someone to, or also even if you don't get stuck, that you have someone else's work to check against. So of course, I'm not going to judge, but don't deprive yourself of taking the opportunity to practice doing the differential equations part on your own. Our first example is mixing. So at a time t naught, or time t equals 0, a tank contains q naught pounds of salt dissolved in 100 gallons of water. Assume that water containing 1/4 pound of salt per gallon is entering the tank at a rate of r gallons per minute, and that the well-stirred mixture is draining from the tank at the same rate of r. Set up the initial value problem that describes this flow process. So the different things we want to do, in addition to setting up the initial value problem, is find the amount of salt Qt in the tank at any time t, or find the equation, and also find the limiting amount Q sub L that is present after a very long time. Last, if r is equal to 3 and Q naught is equal to 2Q sub L, find T after which the salt level is within 2% of Q sub L. Also find the flow rate that is required if the value of T is not to exceed 45 minutes. To start this problem, we want to find Qt, the salt at any time t, but what we want to start with is dq dt, how the salt level changes over time, and that's equal to salt in minus salt out. So first we want to set up the initial value problem. In other words, we want to find the amount Q of t of salt in the tank at any time t. So the amount of salt at time t, it's going to depend on, or the change in the amount of salt is going to depend on the amount of salt in minus the amount of salt out. So we can look at the amount of salt in, which is 1/4 per pound, 1/4 of a pound per gallon, at a rate of r gallons per minute. So that means we have 1/4 times r pounds per minute. Our salt out, well, at time t, there is Qt pounds of salt in 100 gallons of water, leaving at a rate of r gallons per minute. So salt out is equal to Qt pounds per 100 gallons, because there's Qt pounds of salt in the 100 gallons of water, leaving at a rate of r gallons per minute, which gives us 1/100th Qt/r pounds per minute. So our change, dq dt, is equal to our salt in minus salt out, which will give us r over 4, minus r Qt over 100 times pounds per minute, where Q sub 0 is equal to Q naught, and that's our initial value problem right here. So here I have written my formula for dq dt, and which is equal to r over 4 minus rq over 100, which gives us dq dt plus rq 100 is equal to r over 4. So I want to consider, do I want to use integrating factors, or is this a separable equation? Well, first, q, just to note, q is linear, so possibly integrating factors. I'll look at this. So I do have, for integrating factors, you want the form dy dt plus p of t times y of t equals g of t. In this case, y is equal to q, so I'm just going to rewrite this in terms of q instead of y. So that would be dq dt equals p of t, this should be plus, I'm sorry, dq dt plus p of t, q of t is equal to g of t. And that's exactly the form we have here, where p of t is equal to r over 100. Since I've decided to use integrating factors, I need to find my mu, my integrating factor, which is the exponent of the integral of p of t dt, which is equal to e raised to the integral of, here my p of t is r over 100 dt, which is equal to e r over 100 times t. I multiply my entire equation now by my integrating factor here. So I have e r over rt over 100 dq dt plus my integrating factor e r over rt over 100 times, where is my equation, r over 100 qt is equal to my integrating factor e r over 100 times t times r over 4. Then I integrate both sides of the equation. And of course, the integral always looks ugly, but it's not that bad because remember, we chose our integrating factor, so this will integrate to be e to the r, our integrating factor, e to the rt over 100 times qt. And that's equal to integrating this side of the equation, 25e rt over 100 plus c. So dividing both sides of the equation by e rt over 100, we get q of t is equal to 25 plus c e to the negative rt over 100. As t approaches infinity, because we wanted to find the limiting amount, ql, that is present after a very long time, so as t approaches infinity, that's a very long time, we can see that t approaches infinity, so this goes to 0, and we're left with 25 pounds, which is kind of what we expect, because as we put in a quarter pound of salt per gallon, and there's 100 gallons, so there's 25 gallons, over time, the water running in is going to displace the original amount, and we will have the 1/4 pound of salt per gallon, so 25 total pounds. Solving the initial value problem, where we have q of 0 is equal to q naught, plugging in 0 into our solution here, this becomes 1, so we have qt is equal to 25 plus c, which means that c is equal to q naught minus 25. So I kind of summarized everything here, my dq dt equation, my initial value, my differential equation, and then when I solved it, what q of t is equal to, and then the solution to my initial value problem. Now I'm ready to look at if r is equal to 3 and q naught is equal to 2ql after time t, find time t after which the salt level is within 2% of ql. Also find the flow rate that is required if the value of t is not to exceed 45 minutes. Taking this kind of one step at a time, if r is equal to 3 and q naught is equal to 2ql, and remember we found ql on the previous slide, which was 25. So in other words, we're looking at q naught is equal to 50 pounds. So something to notice, we start at 50 pounds, and then eventually we get to 25 pounds. That means our concentration, I'm just going to put this little arrow to remind me, the concentration is decreasing. We also have from our previous work, our formula for q of t right here is actually our initial value is equal to 25. In this case, q naught is equal to 50 minus 25. That gives us 25. E raised to the r now is equal to 3 t over 100. So this is where we are. We have our formula for qt. We know that our q naught is 50, and it's decreasing until we get to ql, which is 25. So we want to find time t where qt is within 0.02 of QL. So 0.02 of QL, well, since QL is 25, 0.02 is plus or minus half a pound of salt. And since the salt level is decreasing, we want T where Q of T is at 25.5. So it's within, because it's not going to get down to 24.5, right? Because QL is kind of the long-term steady state. So we want the salt where when it starts decreasing, it gets down to 25.5. And now I can just plug in. It sounds so easy, but like it sounds dreadful. I don't know. Maybe it's dreadful, maybe it's not. Okay, so QT is equal to 25 plus 25 minus 3, and here's our T, over 100, which is equal to, we want it when QT is equal to 25.5. So we can solve for T, and we find that T is equal to the natural log of 0.02 over 3 times 100, which is approximately 103.4 minutes. Again, here I have my summary of what we have found in the previous slides, and then I summarized Q naught is equal to 2 QL, which is equal to 50, and QT is equal to 25 plus 25 minus e to the RT over 100. So we want to find, here, we want to find the flow rate that is required if the value of T is not to exceed 45 minutes. So we want to find R if T is not to exceed 45 minutes. And salt is within 2% of QL. Now to solve this, again, I'm going to use this equation for QT. So on the right-hand side, I have 25 plus 25e to the minus r, because we're solving for r. I plug in my t, 45 minutes over 100. Here, the amount that I want, find the flow rate that is required, and again, we're assuming that we're going for QL, or 0.2% of QL, and that was 25.5. So here's my equation. I'm solving for R. I have the arithmetic here, and I end up with R is equal to 8.69 gallons per minute. And that completes the mixing example. We're ready to go on to the compound interest. So this example is for anyone who plans to have money. So suppose that a sum of money S naught is deposited into an account that pays interest at an annual rate R. The value ST of the investment at any time t depends on the frequency with which interest is compounded, as well as on the interest rate. So financial institutions have various policies concerning compounding. Some compound monthly, some compound weekly, and others compound daily. Assume that compounding takes place continuously. Set up an initial value problem that describes the growth of the investment. To find an equation for S, I'm going to, well, first my initial value, so S at time 0 is equal to S naught. But to find an equation for S, I'm going to set up my differential equation ds dt. So what does ds dt depend on? Again, it depends on the interest rate, and we're compounding continuously. So I have ds dt is equal to our interest rate times the amount of money we have at time t. So the question is, am I going to use integrating factors or separable equations? I have the two forms written here for integrating factors and separable equations, but also just looking at this, I do have a linear equation, a first order linear differential equation, so I'll probably use integrating factors. Since I've identified integrating factors as my candidate because it is a linear equation, I'm going to see if I can put this equation into this form, and I'm going to write this form here so it looks more like this, essentially because instead of y of t, what I have is s of t. So what I want is I want to replace my y of t in this form with s of t. So what I want is ds dt plus p of t times s of t is equal to g of t. So I look at this, and I kind of just do a subtraction so that I move my r s of t onto the other side of the equation, and I can see I have ds dt. My p of t then is going to be equal to negative r, and my s of t, my g of t is going to equal to 0. So yes, I can put this, I can use integrating factors. So starting with our integrating factors, where we identified p of t is equal to r. So my mu of t is equal to e to the integral of minus r dt, which is equal to e to the minus rt. And then I can multiply my differential equation by my mu, my integrating factor. So I have e to the minus rt ds dt plus e to the minus rt r s of t is equal to e to the minus rt times 0, because I've moved this over. So actually this should be a minus. So here's my equation. I can integrate both sides. This side just becomes c. This side here, because of the way we chose our integrating factor, should just be our integrating factor times s of t. And then you can just verify that the derivative of this with respect to t is equal to this. So using the chain rule, we would have the first, what's in a product? The first part of the product, e to the minus rt, times the derivative of the second part. So that's dsdt, plus this second part of the product, s of t, times the derivative here of this first part of the product, which is minus r. Here I have my minus r, e to the minus rt. So I verified that this is indeed the derivative. I have c over here. To get s of t, I divide both sides of the equation by e to the minus rt, and this is my solution here. To solve the initial value problem, so at time t equals 0, I have s naught. That's the amount of money I start with. So plugging in 0 in for t, here I get c times 1 is equal to s naught. So my initial value problem is equal to st equals s naught e to the rt. So this is my solution. To add a little more realism to this problem, if we assume that deposits or withdrawals take place at a constant rate k, the equation ds dt is equal to rs is then replaced by ds dt is equal to rs plus k, which implies that ds dt minus rs is equal to k, where k is positive for deposits and negative for withdrawals. Here is my equation, and as you can see, it's not going to change my mu because my p of t is the same. I then can multiply my differential equation by my mu and then integrate both sides with respect to t. From there, on the left-hand side, I get my mu times my s of t, and then I integrate this and I get minus k over r e to the minus rt plus c. So I divide both sides of the equation by e to the minus rt, and I get s of t is equal to minus k over r plus c e to the rt. Solving my initial value equation again, plugging in 0 for t, this becomes 0. So I get minus kr plus c is equal to s naught, which means c is equal to s naught minus k over r. So I plug that in and I get my initial value solution here. Here I have rewritten my solution from the other side, so I can point out that s of t is composed of these two terms. And the first term, the s naught e to the rt, that is the return on my initial value s naught. Here, the k over r e to the rt minus 1, that's the component that comes from my deposits and withdrawals. And here it is for everyone who earns an income. Suppose that one opens an individual retirement account at age 25. Notice this is a very young age, but there's a reason for this. It's a very reasonable age to assume you start making money. And makes an annual investment of $2,000 thereafter in a continuous manner. Assuming a rate of return of 8%, what will be the balance in the IRA at age 65? Here, S naught is equal to 0. Our rate of return is 8%. K, that's the amount of money we're putting in. Remember, we have our formula here, and K is our deposits and withdrawals. So K is equal to 2,000, and we want to know what happens after 40 years, right? We're going from 25 to age 65. So S of 40 is equal to S naught times E to the RT plus K over R times e to the rt minus 1. So what we end up with after these 40 years is 588,313. And note the investment amount was $2,000 for 40 years, was only $80,000. So of course this is highly dependent on R. So if R was 0.75% instead of 0.08, or no, not percent. If it were 7.5% or 0.75, then S of 40 would be equal to 508. I can't read these numbers. 508,948. And if R was a little bit higher, 8.5%, then S would be equal to 681,508. So one of the things someone could point out is one of the assumptions in our model. We've assumed that return is compounded continuously. and that additional capital is invested continuously. And neither of this is true in an actual financial situation. Banks don't compound continuously. Some do compound daily. So we have also assumed that the rate of return is constant for an entire period. It is possible to consider R and K to be functions of t rather than constants, in which case the solution will be much more complicated. But next we'll compare with the model in which compounding occurs at finite time intervals, so no longer continuous compounding, which is more realistic. But what we will see is that it doesn't impact these final amounts very much. So to compound n times a year, our formula would be S of t is equal to S naught 1 over R over M mt. And I kind of have a little bit of a derivation here. But anyway, so here, the limit as m goes to infinity of S naught, of this formula here, gives us S naught e to the RT, which is our compounded continuously formula. So this is kind of nice to see. But anyway, if we look at this, I didn't do all the calculations, but I put in a chart here so that you don't have to do all the calculations either. But essentially, the table shows the effect of changing the frequency of compounding for a rate of return at 8%. The second and third columns are calculated for quarterly and daily returns. Here we have quarterly because m, number of times per year, is 4. Here m is equal to 365. This is a daily return. The result shows the frequency of compounding is not particularly important. For example, during a 10-year period, here we are, the difference between quarterly and continuous compound is only $17.50 per $1,000 invested, which is less than $2 per year. And the difference, would be somewhat higher for higher rates, less for less rates. So the kind of what this shows is that the compound, even though the compound continuously is not a realistic situation, it really doesn't impact it that much if you're only compounding even at m equals 4 quarterly. But certainly daily gets you even closer. Hopefully what this example has taught you not just differential equations, but also once you start earning an income, you should right away put money into your IRA, even $2,000. And I'm assuming as an engineer, you're going to make a reasonable salary and you can spare $2,000 a year to put into your IRA, and you'll see it grow and significantly. So by the time you're able to retire, you'll have some money. This is probably the best example in this whole chapter because it tells you something very practical. This next example is chemicals in a pond. So consider a pond that initially contains 10 million gallons of fresh water. Water containing an undesirable chemical flows into the pond at a rate of 5 million gallons per year. The mixture in the pond flows out at the same rate. The concentration, gamma T, of the chemical in the incoming water varies periodically with time according to the expression gamma T is equal to 2 plus sine of 2T grams per gallon. Construct a mathematical model of this flow process and determine the amount of chemical in the pond at any time. Plot the solution and describe in words the effect of the variation in the incoming concentration. Again, this is actually very similar to the first one where water was in a tank. So dq dt, Q being our concentration or the amount of chemical per time, is equal to rate in minus rate out. So rate in is equal to 2 plus sine 2t grams per gallon times, it's flowing in at a rate of 5 times 10 to the 6 gallons per year. So this is our 5 times 2 plus sine 2t grams per year times 10 to the 6th. Our rate out at time t, there is qt grams in 10 to the 7th gallons of water, leaving at 5 times 10 to the 6th gallons per year. So the rate out is equal to our Q, the number of grams, times the rate it's leaving right here, which is QT over 2 grams per year. So dQ dt is equal to rate in minus rate out. And we get this equation 5 times 10 to the 6th times 2 plus sine 2t minus qt over 2 and Q naught is equal to 0. To make our lives a little bit easier, we're going to have this new function, little q of t, which is big Q of t divided by 10 to the 6, so we don't have to have all these exponents and things. We'll have our formula then becomes dq dt plus 1/2 q of t is equal to 10 plus 5 sine of 2t. So that comes from here. So I've summarized everything here. Our dq dt is rate in minus rate out, how we got rate in, how we got rate out, and then dq dt is here, and then we substituted so that little dq dt is basically this expression divided by 10 to the 6, so we could get rid of this here. So we have dq dt plus 1/2 q of t is equal to 10 plus 5 sine of 2t. Q naught is equal to 0. So now we have to consider, should we use integrating factors or separable equations? And I look at this and I see that y, which is equal to q, is first order. We really don't care that t is in a sign. We're just concerned about y being linear. So this is a linear differential equation. Again, we don't care that the t is nonlinear. It's just that the y is linear. In which case, now we can use integrating factors. Again, this is a lot like the first example, the mixing example, so we kind of suspect you're going to use the same sort of approach. Again, don't let the sign of 2t throw you off. We're only concerned about y, or in other words, the variable that also changes with time. We're only concerned about q. And now that we've identified q, then this 1/2 must be our, what is that? The thing that goes in front of the y of t. So then mu is equal to e raised to the integral of 1/2 t, which is equal to 1/2 e to the 1/2 t. So we multiply our entire equation by our integrating factor. We integrate, so we integrate, and then we get this equation here. Oh, I see. This was kind of a this part was a little bit difficult to integrate. This one's easy, right? It's just our integrating factor times q of t. This part was a little bit difficult, so I wrote the equation here, so you could just plug it in here. On the next slide, I have the derivation of this, but here it is. You can just use the formula, and then we see that q of t dividing both sides by e to the t over 2. This is our final formula for little q of t. And here is that integral that is done on the previous page. And remember when I told you the integration by parts formula is really useful? So it really is, because you integrate this by using integration by parts twice. So I have it written out here in notes, so I'll let you take a look if you'd like, but I'm not going to go through it. So going back, this was our solution. Plugging in our initial value, so q at t equals 0 is equal to 0. Plugging that into here, I have 20. I have sine of 0 is 0. I have 1, so I have 20 minus 40 over 17, and then here I have 1 is equal to c. So I have c is equal to 20 plus 40 over 17, so c is equal to minus 300 over 17, and I have sort of a graph of this here as well. So now we have done chemicals in a pond, and we are ready to go to escape velocity. Escape velocity. A body of constant mass m is projected away from the Earth in a direction perpendicular to the Earth's surface with an initial velocity of v naught. Assuming there is no air resistance, because I guess you've taken physics class, but taking into account the variation of the Earth's gravitational field with distance, find an expression for the velocity during the ensuing motion. Also find the initial velocity that is required to lift the body to a given maximum altitude, Amax, above the surface of the Earth, and find the least initial velocity for which the body will not return to Earth. The latter is called the escape velocity. So here is my diagram. Here's the center of the Earth. This is the radius of the Earth, so this is the surface of the Earth. Here we are tangent to the Earth, but we have something projecting out, x, perpendicular to the Earth's surface. And so this is our mass here, and it's getting pulled back with these equations here, which we will derive. So again, the positive x-axis points away from the center of the Earth. That's this axis here, along the line of motion with x equals 0 lying on the Earth's surface. So here's x equals 0. Oh, I'm sorry, x equals 0 is here. The figure is drawn horizontally to remind you that gravity is directed toward the center of the Earth, which is not necessarily downward from perspective away from the Earth's surface. The gravitational force acting on the body is inversely proportional to the square of the distance from the center of the Earth and is given by W of x is equal to minus k over x plus r squared. So inversely proportional of x plus r squared. X plus the radius squared. Actually, this squared should be outside, I believe. I'll check that. Oh yeah, it should be. So on the Earth's surface, W of 0 is equal to negative mg, where g is the acceleration due to gravity at sea level. Therefore, k is equal to mgr squared, and W of x is equal to negative of mgr squared over r plus x squared. And finally, since there are no other forces acting on the body's equation of motion, the equation of motion is m dv dt is equal to minus mg r squared over r plus x squared. And the initial condition is v at time 0 is equal to v naught. And by the way, I had fixed this squared so it's outside the parentheses. Before it was inside the parentheses, and I had commented on it that it was in the wrong place. But then I fixed it, and I fixed it for the beginning of my talk. So it always looks right, even though I'm talking about it being in the wrong place. So here's the equation where we left off on our last slide. So we basically have mass times acceleration is equal to minus mg r squared over r plus x squared. So you might recognize this from physics. We haven't even gotten to the differential equations part, but this is what's kind of interesting. To reduce the number of variables in the equation of motion, we will eliminate t from the equation by thinking of x, the position, the height, as the independent variable. Then we can express dv dt in terms of dv dx by using the chain rule, because dv dt is equal to dv dx times dx dt, which is equal to, here we have v times dv dx, right, because dx dt is v. So the equation of motion now becomes v dv dx is equal to minus g r squared over r plus x squared. So now we only have two variables, x and v. And not only do we have two variables, we have x, and then we have v, which is dependent on x. So we have this lovely differential equation in the form that we're kind of used to. I have the equation here, and I rewrote it here. So we have v dv dx is equal to minus g r squared over r plus x squared. So this is separable, but it's not linear, because in this case x is squared. But we can still separate it. We can still use kind of that technique of separate and then integrate. So here we have only the x variable. Here we have the v variables, so we've already separated. So we can integrate both sides with respect to x. On this side, I'm going to get 1/2 v squared. On this side, I'm going to get g r squared over r plus x plus c. So that will give me v is equal to the square root of plus or minus 2g r, v is equal to plus or minus the square root of 2g r squared over r plus x plus c. So this is our solution, our implicit general solution. Looking at the initial value at x equals 0, t equals 0, and v at t equals 0 is equal to v naught. So plugging in v naught for v and 0 for x, I get v naught squared is equal to g r squared over r. And then also, if I divide this by 2, I get 1/2 v naught squared is equal to minus g r squared over r plus c, which tells me that c is equal to v naught squared over 2 minus g r. Plugging that back in for c here, I get the implicit initial value solution, which is v is equal to plus or minus square root of v naught squared minus 2gr plus 2gr squared over r plus x. So this gives velocity as a function of altitude x. The plus sign is chosen if the body is rising away from Earth. So I have all of this summarized here, my differential equation, how I integrated both sides, how I got my implicit general solution, and then how I plugged in x equals 0 and v equals v naught to get my implicit initial value solution. So now I can continue with A max. So A max is once we have this initial velocity, when we finally get to v equals 0, our maximum altitude. So set v equal to 0 into this equation, and that will give us, when we solve the algebra, somewhere we have A max is equal to v naught squared over r divided by 2gr minus v naught. And last, the escape velocity. We get that by setting A max as A max approaches infinity over here. What we get is this will approach, what will it approach? It'll approach 1, right? Because the r becomes less and less significant. So then we get v naught is equal to the square root of 2gr. And again, just to remind you, this calculation ignores air resistance. Okay, so now we've done 4 examples of using differential equations, first order differential equations, and actually all of them ended up being linear, first order linear differential equations. So we used the integrating factor for all of these, but you have seen that there are differential equations that occur in the real world. So that was a long video, but thank you for watching.